Problem 13 in Chapter 5 is a product mix problem with an integer requirement. To begin, we'll take a look at the first part here, where we're trying to determine how many salespeople to assign to two different regions. So our decision variable x sub I will be the number of salespeople to assign to region I. We're going to try to do this at the maximum profitable way. We know that the average sales for salespeople in Region 1 is $85,000 per year, Region 2 $60,000 per year. So our objective function is going to be max z equal 85,000 x1 plus 60,000 x2. And if we'd like, we can get rid of some of these zeros, as long as we keep in mind that all of our costs are going to be in thousands of dollars. Constraints. We have two resource constraints. We have a budget of $72,000, and we have 10 salespeople. So our first constraint, x1 plus x2, has to be less than or equal to the 10 salespeople that we have available. And the second constraint, 10,000 x1 plus 7,000 x2, has to be less than or equal to $72,000. For non-negativity, x1, x2 have to be both greater than 0 and integer, because we don't want to assign half a person to one region, half to another. Part 2 makes this a little bit more interesting. This is the fixed charge part of the problem. The way this is presented, if we decide to open an office in Region 1, we have to fund that office at $18,000 per year. So what we'll do is we'll define an additional decision variable, y1, and that y will represent the decision to open that office in Region 1, and if we open it, that means we're going to accept that annual cost of $18,000. Now this binary decision variable will go into our objective function, which now becomes max z, profit or sales, equal 85 x1 plus 60,000 x2 minus 18,000 y1. In order to link these two decision variables together, we have to link the number of people that we're sending to Region 1 with the decision to open Region 1 and accept that fixed charge. We need a linking constraint. So we're going to add a third constraint to the problem. We're going to link x1 and y1 together. And what this will do is, if we send anybody to Region 1, that will make x positive, and the only way that this constraint will be satisfied is for y to go to a positive 1 value, to take on a value of 1. Now, in order to get this into a spreadsheet, we have to come up with a value for m, and we can take a look at our two constraints to figure out what that value of m is going to be. We have two constraints. One is the number of salespeople. We have 10 salespeople, coefficient of 1 over here, so based on this first constraint, x1 can be as large as 10. $72,000. Each person in Region 1 takes $10,000, so we can assign up to 7.2. Between the two, x1 can be as large as 7.2. So, for big M, we're looking for the min of 10 divided by 1 or 72 divided by 10, which is 7.2. And we can rewrite this constraint x1 minus 7.2 y1 less than or equal to 0, not putting any further constraints on how big x1 can be. The final two constraints that we have to set up are X decision variables have to be both greater than or equal to 0 and integer. Y1 has to be binary. And that's our complete problem. I'm just going to set this up for part 2 of the problem. Sum product decision variables, comma, coefficients. I can copy this down, pasting only the formulas. And I do need to make one minor change to this, minus this $18,000 fixed charge. My link is my X decision variable minus my binary decision variable times big M. Now to bring this into Solver, we are going to maximize our sales target cell by changing cells X decision variables, the number of salespeople that we're moving, Y decision variable, the decision to open region 1, subject to several constraints. We have our resource constraints. We have a linking constraint. We have to force our decision variables to take on integer values for the X decision variable. And our Y decision variable needs to be binary. Options, linear and non-negative. And for our decision, we decide to move 10 people to region 2, nobody to region 1, and we do not incur that fixed charge up front.